For the kind introduction, and thank you all for attending my presentation. My name is Sunuk Kwan, and I'm from UBC of Canada. This research was conducted under the guidance of Professor Ans and Professor Irani and was supported by Natural Sciences and Engineering Research Council of Canada. Let's get started with the motivation of this research. We often imagine mixed reality scenarios where virtual displays or interfaces float in space or attached to physical surfaces. However, these interfaces are usually flat, so they do not adapt well to complex environments. For example, when an interface blocks a plant on a desk, user cannot utilize the empty space around the object due to the interface occlusion. So it can constrain user movements, such as hand movements. As a result, to place the interface, users need to search for unused flat areas. To support this kind of environmental integration, prior research have mainly represented interfaces either attached to surfaces or positioned in midair through optimization. Also, many positioning techniques have enabled flexible spatial computing, but flexible positioning for surfaces that support environmental understanding have not been widely explored. To support environmental understanding, we formulate the scope of problem into several aspects. First, the issue of occlusion that blocks the user's view. Second, recovering unused empty space that is hidden behind the interface. And third, recognizing the objects behind the interface. But if we try to solve these problems by directly overlaying interface onto physical surfaces, a new issue arises where the interface itself becomes difficult to perceive. Therefore, to address environmental understanding, we need to simultaneously consider occlusion, available space, and shape awareness, and screen quality. And these issues can be reframed within a conceptual framework with mid-air and on-surface interfaces representing two ends of the spectrum. In our work, we explore the space between them to address these challenges. So we introduce draped surfaces which address these four challenges simultaneously. Draped surfaces expand the interface's representational space, allowing them to flow smoothly in response to the environment. As a result, conventional two-dimensional interfaces can be directly extended into any spatial context while remaining compatible, enabling interfaces to be placed in general environments regardless of their geometry. This reduces interference from virtual displays and supports diverse interactions between users and their environments, including virtual physical realities, as well as cross-reality experiences. In summary, draped surfaces extend conventional computing environments into everyday context, providing an expanded representational space that supports environmental understanding. Now let's take a look at how to design draped surfaces. Draped surface can be broadly divided into two stages. First is the initial shape formation, and second is the smoothing process. But to choose the right level of smoothing, we chose to quantify both the available space and the screen quality as the key design consideration. For the user's available space, we define the available space as the volume in front of the interface, using a flat interface as a baseline where the value is a 0. Then we further define the maximum available space as a foreground volume when interface is fully attached without leaving any empty space. The range between these two captures the information about available space. For screen quality, we assume that the ideal screen shape is one where the screen elements are evenly distributed. So when the screen is non-uniform, as shown here, it cannot achieve the maximum screen quality. On the other hand, when the screen shape is uniform, it can achieve maximum screen quality. For detailed equations, please refer to the paper. From these parameters, we can infer the relationship between available space and screen quality across the spectrum between non-flat and flat interfaces. We connected these using a smoothing method to represent intermediate forms. As we expected, we confirmed those relationships from actual simulations. Another remaining question is how much we should smooth. To choose the proper smoothing level, we investigate the cross points between these two lines called balance points and we conducted experiments based on these points for comparison. So overall evaluation includes a simulation study as well as 2 user studies testing occlusion, available space, shape awareness, and screen quality. Let's start with the simulation study. For several objects, we examined how occlusion and available space changed as smoothing was applied. By performing smoothing iterations for each object, we observed that as the interface becomes flatter, occlusion increases and available space decreases. Also, in more general environments, we similarly confirmed that in the draped condition, occlusion decreases while available space increases. This suggests that the draped interfaces can support a wider field of view and provide more available free space. Next, we designed user study 1 to evaluate how the available space can be used. When users perform tasks while looking at an interface, it becomes difficult to access area behind the interface. For example, let's say the user needs to grab a tool located behind the interface on the right. In the case, the user would have to detour to reach the object. Then one might ask, why not just use a transparent display to better access available space and reach objects instead of using draping? To address this question, we designed a similar experimental setting and conducted a task in which participants move their hands between objects under 2 factors, opacity and surface configuration, along with the additional condition without any interface. To examine the detour effect, we measured the trajectories. The left shows the movement path between 2 target positions, and the right presents the results for each condition. The upper 2 are flat conditions, while the others represent the draped and no interface conditions. The conditions are color-coded in a rainbow order. And our results shows that flat interfaces show the larger detour in all hand movement paths, regardless of transparency, which means that the transparent flat interfaces are not sufficient for effective interaction. Next, in user study 2, we evaluated shape awareness and screen quality. So humans naturally have the ability to infer objects behind surfaces. Previous studies have shown that people can reason about objects covered by clothes. So we wanted to investigate whether this recognition ability for background objects applied to mixed reality environments. In addition, prior work has evaluated the legibility of screens on non-rectangular 2D surfaces. We extended this by evaluating whether legibility is maintained on arbitrarily curved draped surfaces. For shape awareness, we tested 6 different objects with multiple choice questions, and our results shows that users could still effectively infer background objects even with draped interfaces. For screen quality, we measured the legibility and found that the draped condition was not significantly different compared to flat interfaces across background objects and drape level. Please refer to the paper for more detail. So these results suggest that draped surfaces can enable both shape awareness and legibility, making them effective user interfaces for supporting environmental understanding. In conclusion, we addressed the 4 key challenges for environmental understanding: occlusion, available space, shape awareness, and screen quality, and approached them using quantitative measures that reflect surface design consideration. Also, our draped surfaces approach enabled the flexible placement of interfaces on complex, arbitrary surfaces, thereby supporting an extended workspace in spatial computing. Thank you for your attention. I'll be happy to take any questions. Thank you.